We present visual odometry transformers, a modality-agnostic odometry framework that can deal with scenarios when modalities are missing, sensors fail, or are intentionally looped out. Animals and humans localize themselves using a variety of sensors depending on the situation they're in. So you might rely on touch when trying to find your phone in a dark bedroom, or you rely on your hearing when traversing traffic. Furthermore, animals use sonar or an internal compass. While sensor fusion tries to utilize all at once, it doesn't take into account that not all modalities are accessible all the time. For example, an iPhone cannot use the LiDAR all the time due to its active nature, consuming more energy than the passive RGB sensor. Another phone might not even have LiDAR to begin with, making it impossible to reuse existing models trained on RGB and LiDAR together. We formalize the problem as a multimodal point goal navigation. In this scenario, the agent has to navigate to a goal, which is given to it at the beginning of an episode. To successfully reach the goal, the agent has to update its position based on sensory observations. Observations and actions experience noise, such that there is no direct mapping between displacement and actions. Using sensors like GPS and compass, this task has been solved with over 90% accuracy. However, GPS and compass are quite unreliable in indoor sensors. Visual odometry is a way to localize the agent from RGBD. In practice, this can also be unrealistic though. Consider the following scenario. During training, you're given access to RGB and depth. But during deployment, your agent might lose access to RGB or even the LiDAR sensor. Also, sensors can run at different frequencies, making it difficult to fuse their information. Recent deep visual odometry methods, or SLAM approaches, require a fixed set of modalities to function. Such restrictions limit their reusability or require multiple models at inference that can deal with each modality combination. We present visual odometry transformers, a modality-agnostic training framework that can deal with such diverse or changing sensor suites and enable agents to navigate successfully in such challenging scenarios. Through our token-based transformer architecture, our method is not limited to visual modalities, but can be extended to arbitrary input modalities like LiDAR, IMU, etc. Since training the architecture from scratch is quite expensive, we employ multiple techniques to reduce the data requirements. We use the action taken by the agent as a prior to prime the model to attend to regions in the image of interest. We pre-train our backbone using multi-MAE, a multimodal multitask pre-training method. To facilitate modality invariance during deployment, we train the agent by randomly dropping modalities, preparing it for what to come. In our evaluation scenario, RGBD is available during training, but modalities are dropped during test time. We evaluate a VOT trained using RGBD with and without modality invariance training. The visualization shows a top-down map of the agent navigating from the start, denoted in blue, to the goal denoted in green. The shortest path is also denoted in green. By taking actions in the environment, the agent follows the blue path. Note the red path overlaying the blue path. This is the imaginary path, the one the agent thinks it took due to its visual odometry estimate. The visual odometry transformer without explicit modality invariance training accumulates drift over time when RGB or depth are missing. This is indicated by the mismatch between the actual blue path and the imaginary red path. Our odometry model trained to be modality invariant is still able to localize efficiently, and the agent successfully navigates to the goal even when depth and RGB are missing. We show that with our proposed technique, the visual odometry model recovers the performance of visual odometry models trained on a single modality alone. This means that a visual odometry transformer trained on RGBD recovers the success rate of a single model trained on RGB or depth alone. To showcase the performance against previous methods, we revisit the habitat point nav challenge. VOT outperforms all prior methods using only 5% of the training data. Note that in the comparison where we drop modalities, baselines based on convolutional networks fail since they expect a fixed set of modalities as input. We visualize the attention map of the VOT. The model attends to image regions relevant to the action taken. For example, when turning, it only attends to regions present before and after acting. Vice versa, it attends to the center region whenever a forward action was executed. To summarize, VOT is a versatile multimodal odometry framework that can deal with optional modalities, that is, modalities that might be unavailable during test time or are intentionally looped out due to expensive active sensing. We propose explicit modality invariance training, which allows VOT to become modality invariant during test time. Finally, providing action information directly to the model acts as a very strong prior. In combination with multimodal pre-training, we drastically reduce the data requirements to train deep visual odometry models. Thank you for your attention. Check out our website with more visualizations and code.